Today is May 14th, and we're going to talk about net change, okay? And a lot of the stuff that we're going to look at today is really stuff that we are already covered, so it's kind of nice for the AP exam, okay? So this normally is taught before we start preparing for the AP exam, so hopefully this goes pretty quickly for you, and it's pretty easy, okay? So example one is from the 2004 exam, okay? Traffic flow is defined as the rate at which cars pass through an intersection, okay, measured in cars per minute. Okay, so cars per minute. Okay, that's a rate, right? So this is going to be a derivative, okay, even though we're not using the derivative notation, okay? The traffic flow at a particular intersection is modeled by the function f, defined by f of t is equal to 82 plus 4 sine t over 2 for 0 less than or equal to t less than or equal to 30, okay? Where f of t is measured in cars per minute and t is measured in minutes, okay? So this is a rate, right? Because this is cars per minute, okay? To the nearest whole number, how many cars pass through the intersection over the 30-minute period? Okay, so from 0 to 30, right? So we're going to want to get how many cars, right? How do you get from cars per minute to just cars? And that's an integral, okay? So here we go. So what we want to do is we're going to write up this integral from 0 to 30 of f of t, right? F of t dt. Okay, why? Now this f of t is cars per minute. The dt, that's the change in time, right? That is minutes. So when you have cars per minute times minutes, okay, that's going to be the number of cars, okay? So this is equal to the integral from 0 to 30 of, okay, I'm going to use parentheses, 82 plus 4 sine of t over 2, close the parenthesis for the t over 2, close the parenthesis for the whole function, and then dt. And then we're going to round to the nearest whole number, okay? So we're going to go to our graphing calculator, and we're going to put this in to do the integral using technology, okay? Okay, so we're going to press y equals, because I'm thinking we're going to use this for other stuff, okay? Clear out any functions you have, and then I'm going to type in 82 plus 4 sine, and then fraction bar x over 2. Close the parenthesis. Okay. And then, okay, so now we're going to go to alpha window, okay, and we want to integrate, so 4. Whoops, I'm sorry. We want to be in the home screen. Ooh, let me delete this. What was I thinking? There we go. Okay, now go to home screen, okay? So go to the home screen. That's what you should do first, okay? Let me just check. Yeah, I didn't mess anything up. Okay, so go back to the home screen, okay? Now, alpha, window, number 4. Okay, so 0 to 30. And then our FFT, which is alpha trace, it was stored in Y1. And we just take the integral with respect to x and put this in, and we're going to round to the nearest whole number. So 2,474, right? So that's what this is, 2,474 cars, okay? We're going to go back, and we're going to record this on our paper. Okay, so this was 2,474 cars. And that's the answer, okay? That's the net change. Yeah, that's that's the net change in the number of cars, okay? All right. So here's the next question. Is the traffic flow increasing or decreasing? Let me slide it up a little bit, okay? Is the traffic flow increasing or decreasing at t equals 7? Give reasons for your answer, okay? So we know it's increasing. We know this thing is increasing or decreasing, right? If the derivative of it is positive or negative, right? And traffic flow is our f of t. It's a derivative, right? It's a derivative of something, okay? Because it's a rate, okay? So what happens when we take the derivative of it, okay? At 7, and that's basically what we want to do, okay? We don't need to do this. This is with the calculator, so we can do everything with technology, okay? So we want to find f prime at 7, right? Because it's asking at t equals 7, okay? And we're going to put that into our calculator, and we're going to see what that comes out to be. Okay, so what we're going to do is we're going to press, from our home screen, press alpha, window, and we want to take the derivative this time, right? And we want to take the derivative with respect to x of y1, because that was our y1 is our traffic flow function, right? So alpha trace and then number 1, and we want to find this derivative at x equals 7. So we put that in, and we get negative 1.873. Okay, so negative 1.873. We'll record this now. So this was negative 1.873. So the derivative at 7 is negative, right? So at that time, that would mean the traffic flow is decreasing, okay? So we would say the traffic flow is decreasing at t equals 7 because, and how do we know it? It's because this derivative, right, f prime of 7, capital F prime of 7 is less than 0. Okay, period. That's it for that one. Okay. All right, so let's go to part C. Okay, so for part C, what is the average value of the traffic flow? So what's the average of this traffic flow basically, okay? Over the time interval 10 to 15. Now, if we integrate, right, we are going to get cars. If we differentiate, we're going to get cars per minute, right? Cars per minute squared. Okay, so we want the average value of the traffic flow. We want the same units as the traffic flow, right? We can do that by integrating because we'll get cars, okay? And then we integrate, and remember it's 1 over b minus a, right? So in this case, 1 over 15 minus 10, okay? And that would be the average value of the traffic flow, okay? So this is going to be 1 over 15 minus 10 times the integral. Now, well, let's just go ahead and write this. 10 to 15 of f of t dt. Okay, so the f of t is cars per minute. The dt is minutes, so cars per minute times minutes is going to give you number of cars. So how are we going to, because we got to get cars per minute back, right? So the way we're going to get that is these right here are time units, right? 15 minutes and 10 minutes, right? So that's going to give you 5 minutes. So we're going to divide by 5 minutes, okay? Which means you go back to cars per minute, okay? So I'm going to clean this up a little bit. This would be 1 over 5, like I just said, okay? Integral from 10 to 15 of f of t dt. And we're going to put that into our calculator, okay? So we'll go back to our calculator and put this one in. Okay, so we're going to do alpha and get the fraction bar 1 over 5. And then go to the right of that, and then we need to do an integral. So alpha window number 4, function integrate, right? And we're going to go from 10 to 15. And then y1. And then dx. So 81.899. Okay. All right. So let's go back and record this one. Okay. So this came out to be 81.899. Okay. And that's the average value, but they also wanted units, right? So when we integrate f of t, this is cars per minute times minute. So this integral is cars, and this 5 is minutes. So this is cars per minute. Okay, and that's the average of the traffic. That's the average of the traffic flow. Okay, so when you say average of something, average value of something, okay, you got to have the same units as that something. So traffic flow, right? Okay. So then part D, let's move on. Okay, so this one, part D says, what is the average rate of change of the traffic flow? So we want to know how the traffic flow is changing, okay? Okay, so this is, we want to find the average rate of change. So this is slope. Average rate of change is slope, okay? So of this traffic flow, okay? And we also want to indicate units of measurement, okay? So this would be F of 15 minus f of 10 over 15 minus 10. Okay, so the units for the top here are cars per minute. And this, okay, so cars per minute is the traffic flow units, right? And we want to know how that's changing per minute, right? And so this is minutes. So this is going to be cars per minute, okay? Or cars per minute squared, okay? So we're going to put this into our calculator, right, to figure this one out, okay? And then we'll come back and record it. And actually, I shouldn't be putting equals here, right? I should be putting approximation, okay? All right, so now let's go to our calculator. So we want to press alpha and then X to get the fraction bar, and then alpha trace number 1 and at 15, and then minus, and then alpha trace number 1 at 10. And then over 15 minus 10 would just be 5, so we could just put 5 there. Okay, and press enter. And 1.5175, so the 5 is going to make the 7 become an 8. So 1.518. 1.518. Okay, let's go back and record. Okay, so this is 1.518. Okay, and what are the units for this, right? So the F units are cars per minute. So we could say cars per minute per minute, okay? Or that's equivalent, because that's a complex fraction, right? So this, you could also write cars per minute squared, okay? Both those units, writing the units both, excuse me, you don't have to write it both ways, okay? Writing the units either one of those two ways would be correct, okay? All right, so that is example number 1, okay? A lot of stuff that we did that should have come back to you because we just took the AP exam, okay? Let's go to the next page and let's do example number 2. Okay, so for example 2, they're giving us the graph of the velocity of a particle moving on the x-axis, shown above, okay? The particle starts at x equals 4 when t equals 0, okay? So that would be, okay, so right now we know that x of 0, okay, the initial position, right, is equal to 4. The velocity is measured in meters per second and the time is measured in seconds. So we know this is seconds and this is the velocity graph. So this is meters and this is meters per second. That's the vertical axis, okay? And so we know, okay, if we integrate, we're going to find the change in position, right? Which is the displacement, okay? So we know that if we integrate and find where the particle is at the end of the trip, right? And the end of the trip is 10 seconds, right? That's the stop, okay? So we want to find, I should say this, we want to find x of 10, okay? What does that equal, right? Okay, so we can figure that out because what we can do is we can integrate, okay, from 0 to 10 v of t dt, and I know, okay, that that's going to come out. The antiderivative of the velocity is position, right? So this would be the position, and we're calling the position the x function, right? X of 10 minus x of 0, okay? I can move the minus x of 0 over here, and I'd have what x of 10 equals, right? So I'm going to write that first, okay? So x of 10 is equal to x of 0, which we know that's 4 from right here, right? Plus the displacement, right? And we did this yesterday, okay? Something very similar, okay? V of t dt. Okay, so this is equivalent to that. We know this is 4, okay? And then plus, okay? Now, all right, so we got to go across, right? We got to do the displacement, okay? And we can, these are all geometric shapes, so these are line segments, okay? So we can use geometry to figure this, the integral out, okay? So if you look right here, okay, you could do this a couple different ways. You could break it up into a triangle here, a rectangle here, and then another triangle, right? And the triangle here and another triangle. Okay, so I'm going to do this first one from 0 to 7, but I'm going to look at it as a trapezoid, okay? So we can just do it in one, from 0 to 7, we can do it in one shot by just doing trapezoid, okay? So we know that the height of the trapezoid is 2, okay? So plus, and the formula for a trapezoid is 1/2 times the height, and we know this height is 2, times the sum of the bases. Well, the first base is from 0 to 7, so that'd be 7. And the bases are always the two sides that are parallel, okay? And then this one right here, this top base, right, is 1, 2, 3. It's 3, right? Because it goes from 3 to 6. That's 3, okay? Now, I'm going to do this area of this triangle, right? But I'm going to need to subtract it because this part of the velocity function is negative. So minus, and the area formula for a triangle is 1/2 base times height. So the base is 2, so 1/2 times 2, times the height, which is also 2. Okay, and then plus, now because this triangle is going to be above, right? So plus 1/2 times, okay, and this base is 1 and this height is 2. So 1 times 2. Okay, so x of 10 is equivalent to 4 plus, well, half of 2 is 1, right? And this is 10, so plus 10. This would be minus 2. And then this would be plus 1. Okay, so x of 10 would equal 4 plus 10 is 14, 12, 13, right? So now we know at the end of the trip, it's at 13 on the x-axis, okay? All right, so now let's go to the next part, okay? And let's go to part B. Okay, so for part D, they want you to find the total distance traveled by the particle, okay? So that's gonna add up the distance that they moved right, along with adding up the distance that they moved left, right? So all of this velocity is positive, okay? Which means it was moving right, then this is moving left, and then moved right. So it went right, left, right, okay? So that means to do this, all right, symbolically, we would have to take the integral from 0 to 10, not of v of t, but the absolute value of v of t dt, okay? And that's going to equal, okay, so this part is going to stay above, right? So it's going to be the same as the trapezoid, right? So it's 1/2 times 2 times 7 plus 3, okay? Now, because I'm taking the absolute value of velocity, this triangle right here actually gets flipped up, right? And it's going to come up here, right? So we don't have to worry about subtracting like we did here, right? We're just going to add, okay, how much it went left. And it went left 1/2 times 2 times 2, and then plus it went right again, right? And that'd be 1/2 times 1 times 2, okay? So this is, again, this is 10. This would be plus 2, and this would be plus 1 again, right? And 10 plus 2 is 12, plus 1 is 13. Now, the 13 we got in part A is a different 13 than we got in part B. 13 is the location on the x-axis. So if you were on the x-axis, you would count 13 spaces away from the origin, and that's the location. So this is the location, whereas this is just a distance, how far it traveled, total distance it traveled, okay? Because it went 10 units to the right, and then it went 2 units to the left, so it still traveled 12, right? If you go 10 right and 2 left, you traveled 12, okay? And then you went 1 right, okay, or the particle went 1 right, okay? All right, let's go to the next example. So example 3 is a table problem, okay? So the last one was a graph problem. The first one was a symbolic problem, right? And the last one, this one is a table problem, okay? And a pump is connected to a generator, operates at varying rate depending on how much power is being drawn from the generator to operate other machinery, okay? The rate, which is gallons per minute at which the pump operates, is recorded at 5-minute intervals for for 1 hour. So how many gallons were pumped during that hour? Okay, so we need to do an integral, right? Okay, so we would integrate, okay, and we could go from 0 to 60 r of t dt. Now, how many gallons were pumped during the hour, right? R of t is gallons per minute, and d of t, well, that's a change in time, right? And that'd be minutes. So gallons per minute times minutes is going to give you gallons, okay? So we can do this by integrating, right? But we don't have a function to integrate. All we have is a table of values, right? So there's a couple ways you could do this. Actually, more than a couple, okay? There's actually 4 different ways you could do this, okay? You could do a midpoint Riemann sum. okay? And why you can't always do a midpoint, all right? But you can go from 0 to 10, 10 to 20, and you always have the one in between, right? 20 to 30, you have 25, 30 to 40, you have 35, 40 to 50, you have 45, and 50 to 60, you have 50. So we could do a midpoint, okay? So this could be approximated by, okay, 10 times R of 5 plus 10. Now that's 0 to 10. So now we're going to go from 10 to 20. So 10 times R of 15 plus 10 times R of, and now we're going to go from 20 to 30. So that'd be 25 plus 10 times R of, okay, and that would be 35 plus 10 times R of 45. And that would be the last one. Now, this is the one that's the minimum, the least amount of work, okay? All right, so this would be, okay, 10 times, and then R of 5 is 60, plus 10 times R of 15, which is 64, plus 10 times R of 25, and R of 25 is 57, plus 10 times R of 35, and that'd be 55, plus 10 times R of 45, which is 60. Right? Because we got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah, we did it 5 times. Okay. So this would be 600 plus 640 gallons plus 570 gallons plus 550 gallons plus 600 gallons. Okay, so I'm not going to add them up. Okay, we know this is give us a number, and it would be in gallons, right? Okay, why is it gallons? Okay, the 10 is minutes, right? That's 10 minutes that went by, and R of 5 is the gallons per minute, right? So minutes times gallons per minute would give us gallons. So each of these is gallons when you multiply it. Okay. All right. Actually, you know what? I'm going to put these in the calculator. I'm going to do it, and I'm going to give you an answer. So hold on a second, and I'll put it in the calculator. 2,960 gallons. Okay. All right, so another way we could do this, okay, we could go 0 to 60. I should say this. This is a midpoint. Riemann sum. Okay. IMRAM, right? Okay. We could also do a left Riemann sum, okay? So if we did we're going to have a lot more entries, right? If we do this one, okay? So if we do a left Riemann sum, okay, that would be 5, and we're going to do so 0 to 5, right? And it's going to be 5, and we're going to do the left one, so it's going to be 58. So 5 times 58, and I'm just going to write the numbers in this time, okay? Plus 5 times, okay, so now we're going from 5 to 10, right? And so it's going to be 60. I'm going to use my finger to hold my place, okay? So 60 plus, and the next one is going to be 10 to 15, and we're going to use the left side, so 65 plus, and there's going to be 10 of these, okay? And then 64 plus 5 times 58 plus 5 times 57 plus 5 times 55 plus 5 times 55, right? We're at this one, right? And then plus 5 times 59 plus 5 times 60 plus 5 times 60 plus 5 times 63. Okay, and we're stopping at this one because we're doing a left Riemann sum, right? So this was a left Riemann sum, or LRAM, okay? All right, we could also do what? A right Riemann sum, okay? So I'm not gonna do that one, okay? And then what else could you do? You could do a trapezoid, right? So I didn't tell you how to do one of these, right? So it's really gonna be your choice, okay? It's your choice on how you want to do this, okay? All right, guys, that's it. Let me go to the let me go to the assignment sheet and I'll tell you what to do for homework. Okay, so today we did integrals as net change, okay, and from data, okay, and graphs. And I want you to do assignment 9-2, which is page 390, and I want you to do 17 through 22 all, and then also number 27. Okay, you guys, four more assignments. We're done for the year. Okay. All right. I really want to encourage you to do these. If you are planning to take second semester calculus, they're going to expect you to know this stuff. Okay. Really, they're going to expect you to know this stuff. Like, okay. So make sure you understand. You may not have the thorough knowledge that I wish you had because I'm not testing you, right? And a lot of times the learning happens right when you have to study for the tests. And I get that. Okay. All right, guys. You have a wonderful day. Proud of all of you. Hang in there. Take care. Bye-bye.